Good morning, class. So for this video, the topic is buoyancy. That's what we will discuss today. Before I discuss that, let's watch a video. It's 3-minute long video, but you will find it very useful. Let's watch that.
Some of the best opportunities to learn are the moments in which we are perplexed, those moments in which we begin to wonder and question. These moments have happened throughout history and led to some truly amazing discoveries. Take this story, for example. There once was a fellow named Archimedes, who was born in 287 BC in the city of Syracuse in Sicily. He was a Greek mathematician, physicist, engineer, inventor, and astronomer. One day, Archimedes was summoned by the king of Sicily to investigate if he had been cheated by a goldsmith. The king said he had given a goldsmith the exact amount of gold needed to make a crown. However, when the crown was ready, the king suspected that the goldsmith cheated and slipped some silver into the crown, keeping some of the gold for himself. The king asked Archimedes to solve the problem, but there was a catch. He couldn't do any damage to the crown. One day, while taking his bath, Archimedes noticed that the water level of the bathtub rose and overflowed as he immersed himself into the tub. He suddenly realized that how much water was displaced depended on how much of his body was immersed. This discovery excited him so much that he jumped out of the tub and ran to his newspaper shop. He found to be assaulted. Archimedes needed to check.
Okay, so that was the Archimedes principle that when a body is placed in a static fluid, it is buoyed up by a force that is equal to the weight of the fluid displaced by that body. So there can be two different cases. One can be one where the body is submerged. Another type case can be where the body is floating on that fluid. So let's discuss the first one where the body is submerged. So we will have few things here. At first, this is the object A, B, C, D. Okay, this is the object here. And when that object was placed on that fluid, obviously due to its weight, it went downward direction. So it actually placed this amount of. Okay. Now, for this one, from our principle, Pascal's law, we know, not the Pascal's law, sorry, for like when something is below the fluid, like inside the fluid, obviously there will be pressure from the fluid. Now let's check the surface ABC, okay? Surface ABC. On this surface, you already know the pressure distribution will be something like that. It will decreased with depth, sorry, increased with depth. And there will be a resultant force here, which let's name that as F bottom. Okay. Now there is a surface, top surface, which is ABC. Obviously, there will be force also. The distribution of the pressure is something like that. Okay. And there will be a resultant force also, which is F top. So for surface A, B, C, that is the force you can see there. Now that F bottom and F top, in between these two, what is happening here? Obviously, the difference between these two is actually the weight of the liquid. This object actually displays the liquid, this blue one. So that will be weight of the liquid displaced by one object, and actually that is called the when force FP, which is actually the weight of the liquid displaced by the object. And we can say that, or we can express that as a, how can we find the weight of the liquid displaced by the object? Obviously, it will be this will be gamma of fluid, volume of that will be the buoyant force. And for any other, just like any other force, obviously there has to be a point where it will be like applied. So that is actually called the center of buoyancy. Okay. CB, which is actually the center of or centroid of the volume of liquid displaced by the body. The so it will be applied on the centroid of this displaced fluid. Okay. So that was for the submerged one. Let's discuss the one where it's floating. So again, the principle submerged, and here the displaced volume is obviously this one. See, again, that buoyant force FB is the weight fluid, and we can calculate the weight of the displaced fluid. Since it's a fluid's weight, so obviously we need to use the gamma of fluid. Since it's displaced by an object, so it will be same volume as in that object. So volume should be the CB, and the center of buoyancy will be the centroid displaced so after this we are like we know that there is a relation between the buoyancy and volume relationship. The more volume one object is replacing, obviously the weight of that volume will be higher, and at the same time the buoyant force will be higher also. Also, why we are so concerned about the buoyancy? That because the buoyancy decides whether an object will float or sink. Okay, you can see that in these two examples here. Like one very common example is a piece of steel that will sink, but like a big object made of steel, it will still like float because of this concept. Like when any object displaces something, the weight of that displaced fluid, if it is greater than the weight of the object, it will float. You can see here. This is just a cube, 1 centimeter cube, but this one is solid and it is displacing some amount of fluid. But when you make a hollow steel box, the same amount of fluid, the volume is 10 times higher. So obviously it is displacing 10 times more fluid. So weight of that fluid is obviously higher, right? So that's why when the weight of displaced fluid is equal or more than the weight of the object, it will float. The same principle applies for ship also. And when you try to swim in the water, obviously you face some of the force like which is in upward direction. That is actually the buoyancy force. Okay, so to solve a buoyancy problem, obviously just like a statics, you need to draw a free body diagram here. Okay, so this is the one free body diagram, and we already know that the buoyancy force, it will act upward direction, and the body's weight, that will act the downward direction. So that's how we will start working on our problem. Let's start working on one class example, which is class example 11. Okay, let's read that question. That 135 lb flat bottom container shown below is 2.5 feet wide. Okay, this one, and 6 feet long. Okay, so this one is 6 feet long. Okay, determine the depth of the container will float in the water when it carries the 150 lb steel block, this one, and when the block is suspended directly beneath the container. Okay, so they are asking you to find the depth of the container will float in the water. So for first case, it's D, and for the second case, it's D prime. Now, just what we have learned from that concept, you can kind of tell that which one is actually displacing more water. Here, the steel block is inside the container. So kind of like the whole thing is going down with that much of weight. And obviously, it should displace more fluid than this one. Let's check if we can see that by our calculation. So let's start working on part A, and we have to find out the this one D. Okay, and this is the free body diagram. You can see that buoyancy force is going upward, and since we have two objects here, one is weight of one is block and one is the container. So obviously there will be two weight. So this one is the weight of block and weight of container. So from the free body diagram, if we say this is the y direction, positive, 0, and we have P going upward, and we have W block minus W here equals to 0. Now we need to find out the value for this W block, W container, FP, and on that process, we will know what is actually D. Okay, let's find out that. So, from the given values, the weight of the block was given, which was 150 FP, F, and the container was 135 LB. Now we don't know the buoyant force, but we know that buoyant force is weight displaced fluid. So this amount of fluid for that 6 feet is actually displacing, right? So if I draw this one, if I try to draw that, that means so kind of this amount of fluid is being displaced, right? So what we will do, we will use, we want to find the weight of the displaced fluid. So that should be gamma fluid and volume of object. Okay. So here, obviously the fluid was water and it's FPS system. So that should be 62.4 multiplied with what should be the volume of that object. So this is D, and we also know that this one is 2.5. That means this one is 2.5. That is B, and this one is 6. So the volume should be 2.56 D. Okay, 0. So if I do the calculation properly, it should be, let's check, 62.4 multiplied by 2.56. 936D minus 150 plus 135, 285 equals to 0. So D equals to 285 over 936, which is 0.30. Okay. And this total length of this height of the container was 1.5 feet. So obviously this one is less than 1.5 feet. That means the container is floating, right? Okay. So this one is done. Let's work with part B. This time, the block is actually outside of that container, okay? Now, since we have two objects here, like two objects, they are displacing the fluid, we will have two buoyancy force. So for each one, there will be one buoyant force and the weight will be same again. So let's draw that displaced amount again. So this time, this is one. Container is displacing something, some fluid here, right? At the same time, this block that is also displacing something here. So let's write it down again. We have, this time we have four forces. Fy, two buoyant forces and two weight. So obviously the container plus block, they are going acting upward. Acting downward. Now we already know the value for weight of the container, which is 135. Weight of lb. Okay. Now we don't know the buoyant force for this amount of for the container and the block, but we also know that if equals to weight displaced. Okay. So let's check if we can find the displaced fluid. This part is just like the last part. This one is d prime. This one is 2.5. This one is 6. So the volume is 6 multiplied with 2.5 multiplied with d. Okay. Let's check if we can find the FB. Okay. So FB block is again gamma times volume. Now for this one, so gamma of fluid multiplied with volume of object, right? That's what we know. We know the gamma is 62.4, but we don't know anything about this block, like area-wise or volume-wise. So how can we find the volume of these objects? Okay, so let's see if anything else is given. So in the question, they give what will be the gamma of steel, which is actually weight over volume, right? So from here, we can actually calculate the volume, which is weight over gamma St. Okay, so let's use this one here. That what was the weight for that block? It was 150, and gamma steel was 490. Okay, so that should be the buoyancy force of that block. So let's calculate that. 490 multiplied with 62.4. So that was 19.02 MPa. Okay. So now we have everything that if y equals to 0, so if B container, if and weight of the container 0. So weight of the container is 6.5 prime plus what was that 19.102 and 1. Okay, so times 2.5, which is 15d prime, 19.102, 135.50, which is 280. Okay, so the d prime is 285 minus 19.102 in 15 is 17. So let's check the calculation again. So, oh, okay. So I didn't multiply with 62.4 here. So that should be 62.4 which is 0.284. Again, that one is 0.284 and the total length was depth of 1.5 feet. So it's less than 1.5 feet. So in both cases, the container will okay. So that's the end of buoyancy. In next part, I will cover the stability. Thank you.